In section 2.4, we are working on creating linear models. That's the title of the section in your textbook. You can also think of this as writing linear equations. We've been doing this already in this chapter. We've been given certain information about a line, such as the slope and 1 point on the line, and we've been asked to write the equation. We've been given 2 points on the line, and from there we had to come up with the slope using our formula and then go from there and write the equation. So this is really just an extension of what we've already been doing, but it is dealing with what for some creates a little bit of I don't know, fear and anxiety, because we're trying to interpret information in word problem form, and for some people these word problems can be a little confusing. But I hope at the end of this lesson you'll see that really we're only dealing with two different types of problems, and the thing that makes these problems different is the way in which we are presented with the slope, or the way that the slope is described in the problem. And I hope that after you watch this, you'll have a better understanding of how you can identify the slope, some key words and phrases that will help you identify the slope that is presented in the problem, and then therefore after that be able to come up with the y-intercept. Because ultimately our goal is to come up with an equation. Something's happening to my pen here, so sorry, I'm trying to get this going. There we go. Sorry about that. We're ultimately trying to get an equation written that looks like this. This is the slope-intercept form for a line, linear equation. And so this is our goal. And then in some problems we'll be asked to use this to come up with another final answer. So let's just get started with this particular example. We have this airplane, and we're told that it is descending or coming down. And this is very important. The rate at which it is coming down. This phrase, a rate of 300 feet per minute. Well, that's just another way. When you see phrases like this, where an object, or it could be a person, is moving at a certain distance over time, feet per minute, that's just another way of explaining to you what the slope of the line is. Now, it also matters the direction that the object is headed. The fact that this airplane is descending is important, because that tells me that in just a minute, when we start to get specific about this equation, the slope needs to represent a line that's doing this. My plane is descending, and I hope you see that a line that goes down from left to right should have a negative slope. But overall, I just want you to get used to seeing phrases like this that describe slope as a constant rate of change or movement. All right, and so the next part of this will help me identify the y-intercept, because you can think of the y-intercept as a starting point. Before the plane began this movement, where was it? How far off the ground? And in this case, we're told that it started off, it was at a point of 8,000 feet before it began this rate of change. And so that's just another way, if you want to think of the starting point, that's another way of saying, well, that's the y-intercept. And you can see that if we know the slope and we know the y-intercept, that makes it pretty easy to write the equation for this. And we're going to postpone graphing for now. So my directions say to write and graph, but we're going to tackle graphing later. So on the homework tonight, when you see instructions about graphing, you can just put that on the back burner for now. Okay, so let's review. We know that slope is known or described as rise over run. We're used to seeing that. And the other day in class, I mentioned that slope can also be referred to as delta y. That little triangle there is the symbol, Greek symbol delta, and that just means the change in y, over delta x, the change in x. So those are familiar ways of looking at slope, but today I want to introduce another way. They're all correct, they're just all different ways of perceiving slope, and that is slope as a constant rate of change or constant movement. And some key phrases to be on the lookout for, like 300 feet per minute and 75 miles per hour. That means we're moving at a certain distance over a certain amount of time. Distance over time. Okay, so with that said, here's some review. Remember, our ultimate goal is to write an equation that looks like this. And we've already talked about it in this problem. Since our plane is descending, that has an effect on our slope because it should be a negative number. And in this case, it's the negative 300. The rate of change is feet per minute. So I'm going to plug negative 300 in for m, which is the slope. And why is it negative? Well, because the plane is descending. If it were rising, then we would have a line that goes in the other direction, which would be a positive slope. And we've already talked about how to identify the Y-intercept. That's like the starting point, and in this case, that's 8,000. And to put all that together, we get our linear model. Pretty simple. Y equals negative 300x, slope is negative 300, and then the Y-intercept is 8,000. Okay, again, don't worry about sketching the graph at this point, but I did this example with the class. Now that we have our linear model, let's make some predictions. For example, after, and this is in feet per minute, what is the altitude of this plane? Altitude after 20 minutes. Okay, after 20 minutes of beginning this downward progression at 300 feet per minute, then how would we know the altitude, which in this problem is given by the variable y, after an input or minutes of 20? So pretty simple. We just let 20 replace x in our equation, and we get negative 6,000 plus 8,000, and that's 2,000 feet. After 20 minutes, this particular plane that is progressing downward at that rate would be 2,000 feet off the ground. All right, so again, two types of problems. And the question that you're asking and that will determine whether or how you attack these problems is, how am I given slope? How is slope described? Is it a constant rate of change like this, which makes it pretty easy? The only trick is, the thing to be careful about, you need to read carefully, is your object or person going up, making it a positive slope, or is it going down, making it a negative slope? And then once you've identified slope, they're going to always give you two numbers in this case. The other number, the starting point, will represent the Y-intercept. Okay, so since we're holding off on graphing until later, let's go ahead and look at the other type of problem. Well, when slope is not described as a constant rate of change, we're going to have to figure it out by coming up with ordered pairs that are provided. All right, slope as a computation of ordered pairs on a particular line. Let me show you what I mean by that. Here's an example taken straight from your book. This is actually number 4 on page 81 and use this as a guide to help you with numbers 5, 6, and 7. All right, so what we're told here is there are 2 leaves along 3 inches of ivy vine. There are 14 leaves along 15 inches of the same vine. So I'm not really told specifically that anything is moving at a constant rate of change like I was previously, but I am given some numbers that could be put together as ordered pairs. And if I have a couple of ordered pairs on a line, I can refer to my slope formula, and then that will help me to eventually write the equation. But here's the key, and I've identified it for you in your notes. The question becomes, of these numbers, I've got a pair of numbers right here that are related, 2 leaves along 3 inches of vine. And those 2 numbers are going to be used in an ordered pair. The big question is, which of these numbers represents the x of the ordered pair, and which one represents the y? Well, here's how you always know that answer. I want you to go to the question that is being asked. Whatever it is that the problem is asking you to find out, in this case, the problem ultimately is asking you to determine how many leaves. So since leaves is the unknown that it's up to me to find out, anything in this problem that has a number that talks about leaves, I'm going to identify as y. So the y variable will always represent the item, the quantity that is the ultimate question. How many leaves? It's unknown. And so therefore, everything in this problem talking about a number of leaves, I'm just going to put a little y above it to help me remember how the ordered pairs are going to be set up. All right? Well, if I've identified numbers of leaves as y, then that means everything talking about inches, because there's only 2 quantities here, there's leaves and there's inches. Every number that references inches, I can go ahead and label as x. But this is so crucial. Let y equal the question you are trying to answer. All right? And the ultimate question here, whatever it is the problem is asking you to find out, that's going to be the y variable. All right, so what we've done here is we've basically come up with a couple of ordered pairs. 3, 2, remember 3 is x, 2 is y, and 15, 14. And again, remember, x stands for inches, in this case. Y stands for leaves, number of leaves. Okay, so this should be pretty familiar to us. If we know 2 points on a line, then we know how to find the slope of that line. y2 minus y1, 14 minus 2, divided by x2 minus x1, 15 minus 3. Of course, that's 12 over 12, which simplifies to 1. All right, so we're just progressing through here using our slope of 1 and just one of the ordered pairs. And I'm just going to go with the ordered pair 3, 2. Remember, we're plugging into slope-intercept. And if I choose the point 3, 2, that tells me what to plug in for x, 3. And this is what I'm going to plug in for y, 2. We found the slope earlier. All right, so simplifying this, we get 2 equals 3 plus b. So subtracting 3 from both sides, we get our y-intercept, which is -1. So with a slope of +1 and a y-intercept of -1, I now can write my model. Y equals +1x minus 1. Okay, so it says to eventually answer the question, I'm going to use my model. So please don't just skip over writing the model and try to answer the question. I've been trying to explain to the classes today that to me, writing the model is the most important part of this exercise. And again, model, equation, linear model, linear equation, same thing. But this is more important than answering this question. Obviously, if you miss this, then it's going to cause you to miss the question. But I want you to don't forget about writing the model and just focus so much on answering the question. But with the model, it makes answering the question pretty easy. Okay, so we're going to make a prediction. We're going to answer the question. How many leaves, remember that's the x variable, I'm sorry, that's the y variable, are there along 6 inches, that's x, we already decided over here. Remember, x is inches, y is leaves. Along 6 inches of the vine. So to find the answer to that, we're just going to replace 6, put 6 in place of x. And 6 minus 1, of course, is 5. That's the ultimate answer to this question. So what I've done here is basically given you one example to help you with problems 1, 2, and 3. So hopefully this example will help you with those 3 problems. They're very similar. And then the second example, the one on the back of your notes, should be a good help to work through numbers 5, 6, and 7. So give me the model in each case, and then when asked, use the model to make a prediction or to come up with an ultimate final answer. So I hope this helps you. After watching, if you still have questions, come and see me, and I'll be glad to give you some further help.